Okay, 9.6 is all about choosing which method to use for solving quadratic equations. So what would be the best method? You've been taught 4. You know how to factor by factoring. You know how to extract the root. You know how to complete the square. And you now know how to use the quadratic equation. So here are the different ways that you can determine which method would be the best to use. You're going to extract the root if the equation is given in the form ax squared plus c equals 0. So if it's in this form, or if it's in this form. So basically what you're saying is b equals 0. You know, the bx term or the linear term, all right, there isn't a linear term. So when it's that scenario, you're going to extract the root, okay? Then if it's not that, then otherwise you're just going to write the equation in standard form and try factoring it. Factoring usually is the quickest method. If the quadratic cannot be factored easily, then you can either complete the square or use the quadratic formula. So we're going to do some of these problems and determine which method is best. So here we have the x squared minus 25 equals 0. Notice that's in the same format here. So because it's in the same format, then we want to extract the root. All right? So we would just go ahead and isolate the x squared, or the quadratic term. Then you would extract the root, and remember to put your plus and minus. So x in this case equals plus or minus 5. Now hopefully if you're looking at this, you realize that this is also a special pattern. It's a difference of squares, right? So you know, you could have, because if you recognize it as a pattern, you probably could have very easily just had factored that one. All right, now let's look at the next one. The next one here, this one here is also in the same format. We would extract the root, but the a is not 1, it's 6. So before you do anything, you're going to divide each term by 6. And what happens then is now you end up with a 1x squared minus 4 equals 0. From here then, you can go ahead and isolate square root, take the isolate the quantities, the quadratic term, excuse me, and then you can now take the square root or extract the root, and you get plus or minus 2. Hopefully, again, if you saw this, you would know that that is a difference of squares, which can be also factored easily. But like I said, sometimes it's just easier just to take the square root or extract the root. This one is also in that form. It just so happens that it's a quantity squared. So basically the a is the 2x minus 1. So it's still in that same form, and you're just going to extract the root. Remember, this becomes out of the radicand. Square root of 16 is plus or minus 4. And of course, now you need to solve the equation. So we're going to add 1 to both sides and then divide everything by 2. And then from there we can simplify, and we get either 5/2 or -3/2. So we've been doing all of this, but as you can see, extracting the root when it's this scenario right here, is very, very easy way to solve for x and get your two solutions. Okay, so now let's look at these examples. Let's look at the first one right here. Is it in the form of this? No, it's not, right? It actually has a b term. The b, right, is 10. So we're not going to extract the root. So that means we're going to write it in standard form. It's already in that, and we're going to try factoring. So when you're factoring, what's the first thing you ask yourself when factoring? Is there a GCF? In this case, there is. There's a 2. I'm going to look at what's inside the parentheses and ask if I can factor it. And I can factor it to be a -1 and a -4. set each factor to 0, solve for x, and I have my two solutions. And we've done all this. Then we look at the next one. Okay, it's not in the right forms to extract roots, so we're going to try factoring, and hopefully you realize there's not a GCF. You're going to ask yourself, is there a special pattern? Well, it looks like it might be a trinomial square. Here's a perfect square. Here's a perfect square. They are adding. In fact, this ends up giving me 6 squared. It's the same thing as 36. So if I was to double that 6, does that give me the middle term, 12? Yes, it does. It is a perfect trinomial square. So that means we can then factor this perfect trinomial square. All right? Should be able to factor it very, very easily. Set each factor to 0 and then solve for x. Looking at the last example, is there a GCF? No. Is it a perfect trinomial square? No. So basically, it's not any special patterns. So the only way you can factor that is by trial and error, right? Trial and error, right? So we know that the factors of 3 is 3 and 1. So we have our 3 and 1. And now we need to know what are the factors of 8 that would end up giving us this. So we have the factors of 8, which is 1 times 8 and 2 times 4. Since they're opposite signs, we've got this going on. We also have this alternative as well. But it's even harder because this here was not 1. So this would be one of those cases where, because it's trial and error, you would complete the square or use the quadratic formula, because otherwise you've got to test it out. Excuse me for coughing. I'm going to cough through this whole video. I have a terrible, terrible cold. So negative 2 times x is a negative 2x, and 3 times 4 is 12x. Negative 2x plus 12x gives me 10x. So this factor did give me the middle term when I tested it out. Now I could have gone through several different patterns before actually succeeding at that. But as you can see, I did factor it correctly because I did get that middle term. Set each to 0 and then solve for the unknown. So when you get this scenario where it's trial and error, you really want to use number 3. So let's look at some of those. All right, so if you would look at the top of page 327, they used our last example that we just did on previous screen. And they demonstrated how to either complete the square or use the quadratic formula so that you can compare the methods. Factoring loses its advantage if factoring takes too long, and this is usually true if the factors of A and C are large. Let me give you an example of that, but make sure that you do look at 327 when you have a moment. So here we have this one right here. And if we were to try to factor that, we have to, ask what are the factors of 140 and the factors of 27 combined, that it's going to give us that middle term, 3x. Well, the factors of 140, you can see there's a lot of them. And then the factors of 27, I've got to use my positive negatives. And so this is a trial and error. This would take a long time to figure it out, right? We're doing that trial and error, right? So it would, at this point then, I would use the complete the square or the quadratic formula. So that's one advantage. Let's look at another type that you would use that on. Here we have this equation. I'm going to go ahead and it's not in this format. In other words, b is not 0. In fact, in this case, b is what? 3, right? So that means we're going to try factoring at step 2, right? So we'll go ahead and put it in standard form. And then I want to try to factor it. All right. So I'm using here, I have the factors of 1 and 5, and here I have the factors of 1 and 1, right? So if I go ahead and I factor this, I'm going to have 5x times x. This is a negative, so I'm going to have opposite signs. The factors of 1 is 1 and 1. I'm going to do the check step for the middle term. This gives me 1x. This gives me a negative 5x, which gives me a negative 4x. And it wouldn't help to switch anything. You know, I could try switching the signs. I could make this one positive, correct? And then I could make this one right here negative. And what that's going to do is make that negative positive, positive. But as you can see, we're always going to get 4x. We will never get the 3. So this does not factor. So when it doesn't factor, you're again going to use that complete the square of the quadratic formula. So I'm going to determine what A, B, and C is. I'm going to write my quadratic formula. I always recommend you write that out so you memorize it. Substitute in the values. Simplify now. And then you get your final answer. And so as you can see, it's a very, very difficult answer that we would have never gotten if we hadn't used the quadratic formula or if we had completed the square. So if you look at page 218, there's a table A. It's called using the discriminant to determine factorability. So here's a quick way for you to determine, should I use the factoring method or should I use the quadratic formula? And so you take your given equation, that's the one we had, I think, in the previous section. You've determined the A, B, and C. Then you're going to take that discriminant, and they tell you the discriminant is just taking the b squared minus the 4ac. That's actually what's on the top of the quadratic formula. And so go ahead and plug in your values and then simplify. And when we simplify, we get a positive 29. If you look at that table, what does it tell you? What's it tell you? That if you end up with a positive, and this is not a perfect square, 29 is not a perfect square, so it's positive, not a perfect square, so it's not factorable. So it's not easily factorable. So that means you're going to use the quadratic formula. So that's a real quick way to say, should I use the quadratic formula on this or should I try to factor it? Let's look at another example. Again, here we go. I'm going to use determine the A, B, and C. I'm going to use the discriminant. This is what we're called the discriminant, right? Plug in those values. Simplify real quick. And then go look at that table that's on page 218. And it will tell you that if it's negative, which this is negative, but it's not a perfect square, then basically you would just say no real solution, okay? You don't even factor it anymore. You don't even put it in a quadratic formula. You just stop and say no real solution. So now let's look at these. I want you to test the factorability with discriminants, with the discriminant, okay? And we're going to use these 4. So let's try them. I'll do the first one for you. You can do it right along with me if you want. Basically, I'm going to determine the A, B, and C. Then I'm going to take the discriminant. This is the discriminant, and I'm going to plug in those values. Simplify, and I got 169. And so tell me, what am I going to do? Is 169 positive? Yes. Is 169 a perfect square? Yes. So if it's positive and a perfect square, because 169, 13 times 13 is 169, then it is factorable. And so then they would recommend that you just go ahead and factor it. Use the factor method. Try the next one. The next one, the book doesn't do it this way, but I recommend you do it this way. Go ahead and clear your fractions. So I'm going to multiply everything by 2. And now I'm going to determine A, B, and C, right? Plug those values into my discriminant, simplify, and I get 25. So now this is positive, and it's a perfect square, so it's easily factorable. So just go ahead and factor it, okay? C, well, we're going to have our values here. We're going to plug it into the discriminant, and we get 5. Now, 5 is positive, but is it a perfect square? No. So it's positive, but not a perfect square. So you're going to use that quadratic formula. You're just going to go ahead and use the quadratic formula. So this discriminant is really nice in helping you determine what method might be easier. Should I factor it or should I do the quadratic formula? Let's try this next one. Again, you're going to find your values, plug them into the discriminant, and this time we got a -3, and so it's negative. It is not a perfect square. And so you're just going to stop and write, like we did in the last one in the previous slide, and write no real solution. So the discriminant is very, very helpful.